In the previous video, we had discussed about the atomic radius. In this video, we're going to be talking about ionic radius. Before that, what's an ion? An ion is formed by the loss or gain of electrons. The elements in the periodic table, except for the noble gases, all of them either have the tendency to lose electrons or gain electrons. And when they lose electrons, that leads to the formation of a cation. And when they gain electrons, they form an anion. So if you see over here, this is a hydrogen atom. Now, when it lost an electron, it led to the formation of a cation, H plus, and when it gained an electron, it leads to the formation of H minus. Now, the ionic radius is defined as the effective distance from the center of the nucleus of the ion up to which it has the influence in the ionic bond. Now, X-ray studies have given us the distance, the internuclear distance between the two ions. But unfortunately, we are not able to calculate the exact value of the ionic radius. Now, this is because, let's take the example, sodium chloride. So sodium chloride is an ionic compound and it has two ions, Na plus sodium and Cl minus. Now the internuclear distance is 276 picometer. And this in turn is the sum of the two ionic radii, that is the ionic radius of sodium and that of chlorine. But unless and until we know the ionic radius of one of these two elements, we cannot predict the value of the ionic radius of the other. This is because, unlike our metallic and covalent radius, we just took the bond length and we divided it by 2. That is because both the atoms are of the same element. This, however, is the ionic bond is formed between two different elements. Two different elements means two extents of effective nuclear charge. So we do not know about, we can't assume that the 276 picometer of sodium chloride can be like divided, and that's the atomic radius of both these atoms, because they have variation with respect to the number of electrons, with respect to the effective nuclear charge. So we can't just assume that that's the case. So X-ray diffraction has actually helped us to calculate the bond length or the ionic bond length, but it has not enabled us to figure out the bond individual radii of the ions. Pauling scale is one of the scale which is used to calculate the bond length, the ionic radius. However, we will not be looking into all of these methods in detail. We are more concerned about the generalizations that were made from the ionic radius. First one, size of the cation is lesser than that of the parent atom. Now, sodium, here you have the example of sodium. Sodium is losing an electron to form Na plus, that is a cation. And if you notice, the radius, that is sodium's radius is 186 picometer, whereas Na plus radius is just 95 picometer. Let's look at the electronic configuration of sodium. Here, if you see, the electronic configuration, here you have the outermost shell, it only has one electron. So when it forms the Na plus ion, it loses the electron from the 3s subshell. So what happens is, even if it lost an electron, the magnitude of the nuclear charge stays the same. So it's easier for this nucleus to pull the other electrons close to it because of the loss of one electron. Okay, and that is why the radius of the cation is going to be, or the size of the cation is lesser than that of the parent atom. I'll repeat it again. So when sodium leads to the formation of Na plus, that is the sodium ion, cation, what happens is it loses the electron from its 3s subshell. So that completely gets removed, right? So 3s is empty, which means the nuclear charge, despite that, nuclear charge, the magnitude of the nuclear charge stays the same. So the nucleus is able to pull the electrons close to it. And that is why the size of the cation is less than that of the parent atom. The next one, the size of the anion is higher than that of the parent atom. Now, here if you see, you have fluorine as the example. Fluorine, when an electron is added to fluorine, it leads to the formation of an anion. And if you notice, the radius of fluorine atom is 64 picometer and that of the anion is 136 picometer. Now, this is because, first of all, the electronic configuration of fluorine is the outermost. I'm only considering the outermost. So you have 2s2, 2p5. When the electron gets added, it changes from 2s2, 2p5 to 2s2, 2p6. Now, there are two reasons why the size is going to be bigger. First one, the electron repulsions are going to be higher than 2p5. In 2p6, you have six electrons in its p orbital, p shell. So there is going to be some amount of electronic repulsions. Not only that, the nuclear charge, the magnitude of the nuclear charge is the same. So it will not be able to effectively pull the electrons towards itself because of the addition of an electron. So due to that, the size of the anion is higher than that of the parent atom. So you have F, fluorine, an electron is added to it. So its configuration changes from 2s2 to p5 to 2s2 p6. So the nuclear magnitude of the nuclear charge is the same, but the number of electrons is increasing. So the nucleus is not going to be able to effectively pull the electrons towards itself. And that's why the size of the anion is higher than that of the parent atom. Now, before we go to the isoelectronic ions, first of all, we're going to be considering the ionic radius for a group. And as we go down the group, similar to the atomic radius, the size of the ionic radius is going to increase. So to understand why all of this is again because of it is similar to that of the ionic, the atomic radius. The reason is going to be the same. If you haven't, do check it. Do check out that video in detail about the atomic radius. Now, isoelectronic ions. Isoelectronic ions are the, as its name suggests, ions, which have the same number of electrons in the outermost. Same number of electrons, not the outermost shell. So sorry, has the same number of electrons. But there is going to be a difference in the magnitude of nuclear charge. The reason I say this is because if you see nitrogen, okay, nitrogen's atomic number is 7. So the nuclear charge is going to be +7. And oxygen, on the other hand, its nuclear charge is 8 +8. Fluorine is +9. Sodium is +11. Magnesium is +12. Aluminium is +13. All these elements have a difference in nuclear charge. But when they form ions, all of them have the same number of electrons in that particular ion. So they have 10 electrons. Okay, so aluminium, magnesium, sodium, fluorine, oxygen, nitrogen. When they are in their ionic form, Al+3, Mg+2, Na+, F-, O-2, N-3, all of these have a difference in the nuclear charge, but they have the same number of electrons. So isoelectronic ions have the same number of electrons, but the effective nuclear charge will obviously vary. Now, if you see their ionic radii, if you see nitrogen has the highest radius, whereas aluminium has the least. So it goes in the order aluminium, magnesium, this is increasing order, Al+3, Mg+2, Na+, F minus, O minus 2, and N minus 3. So this is so we as so if you the reason there is a difference in the atomic radius is because first of all, these are anions and these are cations, right? And as we move from one ion to the other, the nuclear charge is increasing, and so the force of the attraction of the nucleus to the outermost shell will be more. So here, if you see, nitrogen has relatively less nuclear charge than aluminium, and that's why the radius of this particular ion is the highest, whereas for this, it's the lowest. With that, we complete this topic. We learned that cation is formed by the loss of electrons, whereas anion is formed by the gain of electrons. The size of the cation is going to be less than the parent atom because the nucleus is able to pull the electrons towards itself more effectively because of the loss of an electron or loss of one or more electrons. Whereas anions, the size of the anion is bigger than that of the parent atom is because of the nucleus is not able to pull in the electrons because of the addition of a particular one or more electrons. And in a group, as we go from the top, as we go down the group, the ionic radius, similar to the atomic radius, increases. And the isoelectronic ions are basically groups of ions which have the same number of electrons, but they vary with respect to the effective nuclear charge or the nuclear charge itself. In the next video, I believe we will be discussing about the ionization enthalpy. Do check it out.